test. Hey! Here we go. It's live. Every lecture that we have this week shall be recorded because of all the youths who are prestigious and going on taking their AP classes and their tests. Okay. We are talking about hydrostatics. This is fluid that is still, fluid that is not moving. Static means not moving. Hydro means water or fluid. Now, this is what we're going to be covering today. A bunch of different things dealing with pressure. We're going to talk about depth for just a second. These are little equations that we're going to see later on. And we have some other situational vocabulary that might pop on up later. Okay. So, first thing, pressure. Pressure, this is our new quantity. It is related to force. Pressure is how pokey something is or how easily it will penetrate something. Pressure is force divided by the area. That is a capital P, capital F, lowercase a. Pressure is equal to force divided by the area. And we have a new unit. Blaise Pascal was the scientist who came up with these big laws about hydrostatics. And so he was able to name the relating to force to pressure after himself, Pascal, which is Newton per meter squared. Okay, so pressure. There are usually two ways that we think about pressure, right? Poking somebody with either a finger or a needle, the less surface area, the more pressure that there is. But also we usually think of pressure as in what case? Yeah, like tires. You know of PSI, pounds per square inch. Pounds is a force. Per square inch is an area, right? So those aren't SI units that we know of, but they are standard units, or they're imperial units that get used. And so we know that pressure not only has to deal with poking something, but pressure also deals with like gas trapped inside of something that is pushing outwards. So take a look at this little thing here. Take a look at this little piston. I'm going to pause the video to get rid of the glare on the board. Wrong tab. Correct tab. And we're back. Okay, take a look at this here picture. We have a piston. How would you describe what's going on here? Somebody describe this to me, please. Callum.
Like the piston surface area is like causing an increase in pressure as it it removes the area for the air to reside
in. I see. Removes the volume for the air to reside in. Yes, two different sorts of things, because we have a cross-sectional area that is being applied, right? So when we think of the pressure from poking something, we have this hand applying the force. And what would the area be when it comes to this pressure? The area is coming from this piston, right? So this area is fighting against the gas that is trapped on the inside. What happens as you press the piston further in? What are you going to feel? It's going to be harder and harder to push on it because the pressure from the gas fights back. It's Newton's third law. Whatever you put into something, something is going to fight on back. Even though you're pressing something like air is still going to fight back because everyone go like this. Everyone go like this. You can feel the air. Okay, that was okay. Liam committed assault. This is not good. So essentially what ends up happening is that this piston is going to get hard to push in because the pressure from the gas on the inside, the gas is going to be pressing back outwards with the same amount of pressure, right? So the pressure that you're pressing inwards is going to be the same amount that the gas presses outwards because of, okay, right? And so what you can think of is this being a bunch of tiny little pistons, okay? We have a container full of gas, and what's happening is the gas is trapped on the inside. It is trying to press on outward, but the container is like this part of the piston. The container is preventing it from going back outwards. What does the gas want to do, everybody, right now? What does the gas want to do? Exactly. It wants to spread out. What is the container doing? It's pressing it inwards. How does the pressure of the container and the gas relate to each other? They're the same, equal and opposite. One is pressing outwards, one is pressing inwards. So, how can we relate poking somebody with a needle as pressure to gas trying to escape from a tire? How can we make the two of them linked together? And the hint is the piston. So think about, why are we able to connect the force of poking somebody with the finger to a tire trying to contain air? How can we relate those two pressures? Jojo, please pull the popsicles.
So when you're like poking someone, it's like you're trying to like push them and reduce their volume, which makes you feel like force. Just like how if you're like pressing on a tire, it'll resist because you're trying to like compress the tire and you're gonna feel force.
I like this. I like this. So you're talking about poking somebody from the outside. Poking, you can think of this as like the external sort of thing. Kel?
We came up with like imagine like 100,000 little candies all with needles poking in the tire, and that's kind of like how it relates to the needle, as that was just one point of contact, like Louise said, but inside the tire there's just like thousands of different points of contact acting against it.
Perfect. Just like we saw earlier with our thousands. Now that I'm being recorded, maybe I shouldn't bring up the exact, but let's think of 1,000 little Kennys captured within this ring and this hoop. They're all contributing to the rotational inertia here, right? And that's just the idea that we can add up all the particles within a shape. Same thing when it comes to our pressure. You can think of these as a bunch of tiny little needles or fingers that are poking inward at the gas, and treating it as, or actually a better example would be like a bunch of tiny pistons that are pressing the gas and keeping it inward. We have the fingers versus the gas. Something pressing inward and something pressing outward. You can give yourselves a point. That was Callum. That was wonderful. Chris said right things. He didn't read my mind though. We know it's not about being right. It's about reading my mind. We know this. So now what we're going to talk about is what happens. Why is it dangerous to go on up to Mount Everest? Because there's hardly any air up there. It's low pressure. It gets harder to breathe up there, right? Because there's less air up there, and air is less dense. Why is it dangerous to go scuba diving?
Because the high pressure kind of force focuses like a lot of nitrogen in the blood.
So it becomes the fact that we have more pressure that we're dealing with, right? So we know that the reason why this is because when you go up on Mount Everest, why is there less pressure up there? There's more space. Yes, that's like the kind of the definition. But why is there less space, or why is there more space between these molecules?
The gravitational field strength is lower, so there's not as much holding air.
It's about bringing the air downwards, right? So essentially, what ends up happening is that the further away that you go, the less air that you have on top of you. Air is just like a book. Remember the example that we had where we had all these books laying on top of each other? Right? Where we can think of which book is experiencing the most amount of force. The bottom book. Because we have the two books on top of that. You can think of these also like air particles, where the more air that you have on top of you, the more that's going to be pressing down on you. And same thing with water as well. The more water or fluid that is above you, the more that's pressing down on you.
How does the nitrogen into the water?
Because you're breathing more of it.
But I thought you're breathing out of like the tank.
The air in the tank gets compressed.
Oh,
and air is mostly made of nitrogen. Air is mostly made of nitrogen. Anyway, we are. Oh geez. Oh gosh. So we're going to talk about depth and how that relates to pressure. Okay. So if you place something inside of a fluid, you now think of yourself as the gas inside the tire. You have a bunch of fluid on the outside. About a bunch of all this fluid is like a bunch of little needles poking you. It's all a bunch of needles, and the deeper that you go, there are needles poking you, but there are needles on top of those needles. Essentially, there are more books being placed on top of you when you go lower underground. And you are being poked at with needles from all directions and is perpendicular to your surface. All these needles poke perpendicular to your surface. Okay. Actually, well, there's more resistive force. There would be more drag. There would be more drag, but also energy transfers easier when molecules are more compact. Uh, you ever see like when you tangent, tangent? I'm on video. I'm on video. Spirit, I'm on video. So, um, taking a look at this. Why is there more pressure the deeper that you go? That's my next question. Why is there more pressure the deeper that you go? Why is there less pressure the higher you go up? Joe, who's answering my question?
So, can you bring up the picture, please? So when you're lower or deeper in the water, there's more water on top of you, and that water that is on top of you is also being acted on by greater force by the gravity. So it's like more densely packed. And when you're higher to the surface, it's like the opposite.
Perfect. So, the way that you can calculate the pressure that is from this water is the same thing. It is force divided by the area. Force divided by the area. The force that we're talking about here is the weight of the water that is on top of you, right? So if we take the weight of this water and we divide it by the surface area of the water, well, we end up volume equals um, uh, the volume of the water is going to be the surface area times the height of the water. The surface area being pi r squared, and then this is the height. But we get that force. The pressure is equal to what? What is pressure equal to? Force over area. So what ends up happening is that the pressure that comes from this water is going to be mg. Exactly, over a mg times the volume divided by a. So we end up getting that. Oh, we'll get to the equations in a second. But it's going to be equal to mgh. Mgh is going to be where this pressure from water on top of you comes from. We talked about that. Now, oh yes, this is important. Now we're going to bring this back to buoyant force. So because we know that the deeper you go into a fluid, the more pressure there's going to be. When you have an object that is here, the water coming in from this underneath the object is going to have more pressure. So because it has more pressure, because it's deeper, that means that there's there's a net force pushing upward on you when you have something that is submerged. So that means that the pressure from this water is, while you feel pressure as something that happens when you go lower, you have a buoyant force that's pointing upward because there is a difference in pressure between the top and the bottom of the object. Kellen.
Kind of going back to I think you talked about you took a semi-circle bowl and placed it in
Yep.
water, and then it was floating, and you asked why.
Mhm.
Is that I know this might be kind of off topic, but does that have to do with anything with the air and holding it
the way that the shape of the object is going to displace fluid a certain amount, and if you have a flatter object, it's going to end up displacing more fluid as you press it on in.
Okay. But what
And so,
about
because you're displacing a lot more fluid uh, with a smaller amount of object, that object is going to be able to float more easily.
what about like an op like you ever like take like those balloons and like you like hold it underwater and it pops back up like really fast? Like what does that look like for this?
Well, it's going to be the same sort of thing where there's a big difference in pressure between the top and the bottom. It's because you have so much air on the inside of the object
So
that you
it's
have.
it's super being like pressed like so many needles or not
It's
really?
yeah, it's not that it's so many needles. It's that the balloon is so light that the needles press it upward really quickly.
Oh, and that can just beat the
Exactly. Last question.
So the pressure is caused by the buoyant force? Is it pointing upwards?
Always, it's you can think of buoyant force as a net force that is upward from pressure, a net pressure that is going
So
upwards.
pressure causes buoyant.
Correct. The difference in pressure causes buoyant force. Now, if we were to place a barometer or a pressure gauge at different points of the volume, if we're at the same height, we're going to experience the same pressure. Same height and the same fluid is going to lead to the same pressure because you have the same amount of fluid above you. Same height, same fluid, same pressure. Say it.
Same height, same fluid, same pressure.
And maybe actually same depth, same fluid, same pressure, but it's a same thing. Okay. Just go ahead and take a second to talk about what you've learned so far with somebody across the room. Exchange a sign of peace. Take 2 minutes. Go. And we go back. So, like I said, we know that as you go further underneath a fluid, you experience more what? Wonderful. Dylan brought up an interesting point. It said that if you brought a scale under the water, would the scale weigh more? Would the scale weigh more? There is more fluid that is above it. However, remember, buoyant force is a net force going which way? It's a net pressure that is upwards. So just because you bring a scale into water, all the fluid that's below it is like the force of this table. The force of the table is the greatest amount of force because it's holding up all this other stuff, right? So when you place this scale underneath the water, you do have fluid pressing down from above it, but the fluid from below it is working even harder than all the fluid that's above it to kind of press it on upwards. And that's why you're getting pressed on in all different directions because that fluid below is also holding up all that fluid that is above. So the buoyant force is a difference in pressure. It is not a total pressure. The buoyant force is a difference in pressure. And because you have one end of the object that is lower than the other, it's going to end up having a netward buoyant force that's going upward. Correct. Because helium is lighter than air or less dense than air.
So when I was hiking like a mountain,
Mhm.
And it's very tall, and I'm wearing like a big backpack.
Yeah.
I don't know, maybe my dad was lying to me, but he was like, I waited at the bottom and I was like, oh, this is gonna be too heavy for me. He said, no, don't worry. When we're all the way up there, it's gonna be way lighter because like you're gonna be higher up. Is that true, or is that
Actually, it's a good segue. That's a good segue because, yes, the weight of the atmosphere is actually holding down on you. How many of you feel like you do well under pressure? How many of you feel like you honestly don't? How many feel it's kind of tough to live up to a certain moment, whether it's sports, whether it's like you start sweating more if it comes to academia and it comes to this time of year? How many of you feel like the pressure can kind of get to you? It's all right. I just want you to know that when you are here, the atmosphere presses down on you for every square inch, 14.7 pounds. And overall, that is 101 kilopascals of pressure. You deal with a lot of pressure just because there is a lot of air on top of you. Right? So you already deal with a lot of pressure to begin with, and you do just fine. What's a little bit more pressure to you? See? We're already built fairly different. Okay. Yeah.
You know, like in the Bolivian, like La Paz, you know, like the Bolivians, when Argentinians or other teams play soccer against them, they tend to do terrible because they get tired quickly. They end up being able to play.
Oh, due to altitude.
That's, you know, like the pressure. What's up with that pressure?
That does deal with pressure. The further up you go, there is less pressure, right? And so essentially, you can what you can think of is we thought of pressure before as a fluid that is a column of fluid that is weighing on top of you, right? When you can think of a column of air on top of you. If that column of air had an area of 1 square inch, it would press down on you with 14.7 pounds. Like a bowling ball is the equivalent of what they're putting there. Okay. So, and if you were to expand this on outward to a square meter, it presses down on you with 10,000. Is that 10,000? 10,000 newtons. Oh no, it's 100,000 newtons. Sorry, 100,000 newtons. It's a lot. For every square meter, it's 100,000 newtons of air. It's ridiculous. So, what this means is that we have a couple different types of pressure. The first one is atmospheric pressure. Atmospheric pressure is pressure that comes from the atmosphere. And pascals are newtons per square meter. So for every square meter, we have 100,000 newtons. You can also, 1 atmosphere of pressure is that same amount, what we feel on the surface of the Earth. Now, if we were to take multiple fluids and stack them all on top of each other, right? We said that if you have one fluid that's on top of you, you're going to feel the weight of that entire fluid. If you are underneath multiple fluids, you are going to feel the weight of multiple fluids. Liquid and gas are fluids. So that means that when you're underneath the water, not only are you holding up the weight of all that water that you're underneath, but you're also holding up the weight of the whole atmosphere. When you're underwater, you're holding up not just the water, but the atmosphere as well. So, and when you take the AP test and you have these FRQs and there's a pressure moment, it's not just the pressure of the AP test, but also the pressure of the atmosphere, pressure of the world, pressure, yeah. So, essentially what you do is you just add up the pressure from all these different objects above you. And you take the weight of all the total fluids divided by that surface area. The weight of the air above you, the weight of the purple fluid, the green fluid, and the blue fluid if you're at the bottom of this. And that's going to be the total pressure. Weight divided by the area. So if I were at the bottom of this beaker, how could I figure out the pressure that I am experiencing using the weight of different fluids? If I'm at the bottom of this beaker, how can I talk about the pressure I'm experiencing from the weight of these other fluids? Jojo, please. And what are the forces I'm experiencing? What we call the force of gravity. Of what? The atmosphere. Well, where am I? I'm at the bottom of this fluid. So is it just the weight of the atmosphere? Yes, it's the weight of all fluids above me. It's the weight of all fluids above me divided by the surface area that it's contained in. It's contained in this little beaker with the surface area, and you take all that weight and just divide it by the surface area. That's going to be the pressure that's in there.
What about the buoyant fluids?
pressure is not.
If we want to find like net pressure, don't we gotta like?
Let me.
Yeah, but if it's at the bottom, there's still some sort of pressure coming up.
Buoyant force comes from the fluid that is moved out of the way.
Yeah, but what about normal force?
That's from the beaker. Like that would be from the bottom of the beaker.
Yeah, so don't we have to include that?
No, right now it's just if it's just asking you for what the pressure is in the fluid at the bottom, then that's it. And pressure is its own thing. Finding pressure from the fluid above you is not the same as finding the buoyant force from the displaced fluid below you.
Okay, so if I'm at the very bottom, there's no displaced fluid anymore.
There is,
So then I don't.
but they're not asking for. But they're not. It's just depends on what you're asking for.
Okay.
Are you asking for the buoyant force, or are you asking in the difference? Are you asking for the pressure at one point? Or are you asking for the difference in pressure between top and bottom?
So difference in pressure, you have to include buoyant force, but pressure at one point it doesn't matter. Oh no, surely it still doesn't matter, right? Because
It depends. Calum, it just depends on what they ask for. Do they ask you for the pressure, or do they ask you for the buoyant force? Do they ask you for normal force? Do they ask you for the force of gravity? They can just ask you for different things. While buoyant force is caused from a difference in pressure, they don't necessarily need to ask you what the buoyant force is. Now we move on. Gauge pressure, right? So we have pressure from the atmosphere, which we call what?
Atmospheric pressure.
Wonderful, everybody. What do we call pressure from the atmosphere? What do we call the total amount of pressure that you're feeling? Absolute pressure. Now, what we call something is the pressure of the fluid, that whatever fluid you're submerged in, and we relate it to the atmosphere. It's like lots of times we think of the surface of the earth as zero. We arbitrarily put zero someplace in order to make it easy, right? In order to make the problem easy. 100,000 pascals of pressure is a lot of pressure. So whenever you deal with a little change in pressure that comes from you going underneath water, that kind of pales in comparison to the absolute pressure, to the atmospheric pressure that's on the surface. That's just a reaction to the air that's inside your body being like kind of having more pressure acting on it. And so a lot of times it's convenient to not say what the total pressure is that an object is facing, but just the pressure of the fluid that's on the inside. And what we call this is, you can call it one of two things. Actually, honestly, one of three things. You can call it the gauge pressure. That's the most common thing it'll be called, the gauge pressure. You could also call it hydrostatic pressure, which is just the fluid with the pressure of the fluid that you're submerged in. Or you could call it the differential pressure, talking about the difference between atmospheric and the absolute pressure. My question for you is, what is gauge pressure? And what are other names for it? And why can you call it those other names? What is gauge pressure? What are other names for it? And why do you call it those names? Jojo, who's going? Wait, sorry, one more time. Oh no, just these are pressure gauges. But what are some other names that we gave to gauge pressure?
Come on, bro.
Huh? Cal. Oh, why are you interrupting? So the barometer is what we call the pressure gauge. But gauge pressure is, you could say it's something that you would read off of a barometer. Yes, that what you read off a barometer is gauge pressure. But I called it two other things. One of them is even on the board. I know the board's a little far away. Ah, yes. Why do you think I'd call it hydrostatic pressure? It's the what? Yes, the water's not moving. Yes, but why would I call this the hydrostatic pressure? Because it is the pressure of the fluid that you're submerged in. That's right. Also, you can call it differential pressure because this, huh?
What is static?
Static it just means not moving. You think when you think of electrostatic, that's something that's different, right? When you think of static, you think of electricity, but static itself means not moving. Yes. Now, so gauge pressure. Gauge pressure comes from the fact that if you would put a gauge underwater, a pressure gauge, a barometer, it would read a certain amount. Because usually when we set zero on those gauges, we set the zero when you're on the atmosphere, when you're in the atmosphere. So when you place it anywhere else, it's going to tell you the difference between the atmosphere and that. Okay, this is the what do you call it? This is the derivation for how we get that the gauge pressure is equal to the density of the fluid that you're in times gravitational field of gravity times the depth that you're submerged underneath the fluid. Because you take the weight and divide by the area, you get the weight from density times the volume. Volume is equal to Look at this density Density times gravity divided by area. Okay. Now, we're going to get into the rules now when it comes to, I know. We exchanged a side piece. We already had a little break. Let's do it again so you can just kind of recap everything that you've learned so far when it comes to pressure. We'll talk about the different types of pressure, where they come from. Go ahead. Okay. Let's see. We have the rules. Fluid, these perfect fluids that we have, these fluids are non-compressible. Incompressible? Incompressible, I think is the term. You cannot take a fluid in like a gas, you can increase the size of a balloon in the container that it's in. When it comes to a fluid, you cannot, right? When it comes to a fluid, the amount of fluid that's there, the volume is not going to be changed based on how much you press on it. The volume the volume cannot be changed in a fluid no matter how much you press on it. Gas, that's not the same. But for liquids, it is, right? Let's do that. So what that means is that any pressure that you put into the liquid is going to get distributed evenly throughout that entire liquid. So for instance, if I just have this liquid right here, this is honey. When I place a barometer inside of honey, it gives me 132 kilopascals because that's the absolute pressure taking into account the air, right? And so if I were to go ahead and add a 500 kilogram weight to it, it would be pressing down on the fluid, and the fluid would get moved kind of elsewhere. In the simulation, it gets kind of moved elsewhere, but the pressure gets added regardless of the weight of this object divided by the surface area. Okay, so essentially, when you add pressure to something, add pressure, external pressure, it's going to get distributed evenly throughout the fluid. That is Pascal's principle, as what it's known as. Pascal, that's what his famous principle is. That's the first thing you have to know. No. Yeah, you're stuck. So now what we have is that is when we have a contained fluid where it only has one end, essentially, like it's just fluid in a container. However, if we have fluid that has two ends, like this, we have a couple different rules that apply. First of all, if a fluid is left on its own and there's no external pressures added to it besides like the atmosphere is pressing down on both ends of this, right? It's not just on one end, but it's on both ends. What that means is that the fluid, what do you notice about the fluid at both of these ends? It's the same height. That's the sort of equilibrium. And in order for a fluid to end up being at a different height on the surfaces, that means that you're going to add a pressure to it, right? So in this case, we have the fluid here being lower than this one because we added this 500 kilogram weight. When we added this weight, what happens to the water level on the other side? It rises up. Okay, so when you add this, it goes and rises on up. Fluid is not compressible. Liquid is not compressible. If I push this towel, the whole towel moves. When I press on the water, the whole water gets displaced. The whole water gets displaced. So, a couple things come from this. If you add pressure to a fluid, this is what we said earlier. Same depth, same fluid, same pressure, no matter what. Even when I added an external pressure here, right, we have at the same heights on two different ends, it's the same pressure, no matter what. And also, when we add this weight over here, the volume of water that gets displaced over here is going to be the volume of water that gets displaced over here, right? So if you take a look over here, we have this. I put the 0 right here. I put the 0 on the surface of the water, and we know that's the same on both sides. Then I come over here, and this is lower down, right, from here to the 1 meter mark. And guess what? On the water level over here, I can't zoom in anymore. Come on. You see, it increases the same volume, not the same height. Why did it not rise up so much? It's a larger what? Area. It's a larger area, so that means that the height is going to be smaller for the same amount of liquid. Okay, so I have shared with you four things. Liquid is incompressible. A change in pressure anywhere is a change in pressure everywhere. Is that, well, that's thanks, Malcolm X. I'm not gonna I'll put that in quotes. A little grain of salt in there, right? A little grain of water in that, but okay. Third is that when a fluid is left on its own, when it comes to having two openings, it's going to have the same height. And then when you add an external pressure, the pressure is going to be same everywhere at the same height for the same liquid. And the fact that the volume that gets changed will come up on the other side. Okay. So we have two different situations. One where we have like a perfectly enclosed liquid, and then one we have liquid that has sort of two ends, two different surfaces. Talk about the rules for the liquid that is enclosed with one surface. Talk about these two rules that I talked about. Go ahead. Okay, now talk about the rules to this over here when we have fluids that have sort of two different openings to it. Talk about it. Okay, gentlemen, last things. Let's go ahead and just talk about the different situations that we have. We'll have situations where we have the water or a liquid with one surface, and then we have these situations with two different surfaces. Now, we said that a change in pressure anywhere is a change in pressure everywhere, meaning that if we change the pressure over here on this side, we're going to change the pressure over on this side. Okay. And so what ends up happening is that the pressure is the same depth, same depth, same fluid, same pressure. Same depth, same fluid, same pressure. So that means the pressures are the same. If you have a smaller cross-sectional area and you apply a smaller force, the same pressure, if you have a larger cross-sectional area, will lead to a larger force. And what is funky about this is because this is why we're able to use jacks and why we're able to lift cars using hydraulics. The power of hydraulics is that the fact that because we're going to have the same pressure on both sides, you don't have to put in that much force. You can have a smaller amount of force with a smaller surface area, but because F1 over A1 is going to be equal F2 over A2, if you increase the A of the other end, that means F2 has to be way larger. Now, the thing is, it's not going to move up as much because, as we said, when you displace the volume over here a lot, this volume is displaced the same amount, but because it's the depth, if you increase this depth a lot, you're going to increase this depth over here just a little bit, right? Remember how much this water sank versus how much this water rose, right? So it's the same thing over here. When you put in more displacement over here, this is going to rise up just a little bit. So that's why when you have a jack and you're cranking it over and over and over again, the car rises up slowly. And that's about it. Same thing with bike pumps, exactly. These are the equations that you'll be using tonight for homework. I was too busy putting this document together that I didn't actually assign the assignments, so that's not out yet as of the time of this video, but they'll be up. This is the equation pool that you're dealing with, right? We have density is equal to mass divided by the volume. We have that pressure is equal to force divided by area. And then we also have over here, what is this a formula for? No, it's not. It's the absolute pressure. The absolute pressure is equal to the atmospheric pressure plus the gauge pressure. Gauge pressure is equal to density times gravity times the depth. They might throw in buoyant force on there, but y'all are prepared. Okay, I'm going to get some both concept questions and calculation-based questions for you assigned on there, and I'll put little examples on that. But that's it. That's it when it comes to pressure and all different things we have to know. I hope you enjoyed this Titanic 42-minute video.